introduction. Yep, my name's Eliott. I'm a first-year PhD student at Newcastle University, and this will be my presentation on how we can use machine learning to increase the resolution of hydrodynamic simulations, which I've been working on in collaboration with my supervisor, Dr. Marika Asghari. And so just for a bit of background, stuff that I'm sure you'll all really know, most of the matter in the universe is dark matter, and that dark matter tends to cluster together in halos due to its gravity. And galaxies as well tend to also locate themselves in those clusters due to the gravity of the dark matter. And so we've got galaxies sitting in these dark matter halos, and the properties of the two are connected, unsurprisingly. So for example, if you've got a halo with a higher mass, then you'd expect to have a galaxy with a higher mass, higher stellar mass in there as well. And so we want to understand this connection because if we want to understand dark matter, all we've got to look at is the baryonic matter that sits within it. And so when we're making an observation, we then need to use a model of the nonlinear clustering, which has been calibrated to simulations to then be able to put constraints on cosmological parameters. So it's really important that we have robust simulations that we can then use to be able to go from an observation to being able to constrain cosmological parameters and then hopefully maybe resolve some tensions. And so let's talk about simulations. So I work with the FLAMINGO suite of simulations, which was developed in collaboration by Durham, Leiden, and Liverpool John Moores universities. It's a suite of hydrodynamic simulations with resolutions ranging from at 10 to the 8 to 10 to the 10 solar masses for particle size, and a co-moving box side length of most of them. The runs have about it's a gigaparsec box side length, but it does go up to 2.8 gigaparsecs box side length. And for all the hydrodynamic runs, there also exists a dark matter only run, which has the same initial conditions and seed, and so it's possible to match things between the two. And these simulations have been calibrated. The subgrid parameters have been calibrated such that they'll match some observables. So for FLAMINGO, it's the stellar mass function and the gas mass fraction that we see in observations. And so when comparing to other similar simulations, FLAMINGO is very much on the larger but low resolution side. So if we look at this plot here, on the x-axis you've got the box side length, so the size of the simulation. And then on the y-axis you've got the minimum particle size, basically, so the resolution increases as you go up the y-axis. And then those diagonal lines correspond to the number of particles in the simulation. So as you move perpendicular to the diagonal lines, effectively the computation time is going up as well, and that's really the limiting factor. So we want to find a way that we can move up perpendicular to those diagonal lines. And so that's where my work comes in. So, well, before what I do, you need to go from these simulations, which is just a collection of particles, to then a catalogue of halos. And that work has already been done, thankfully. And so that's done by a 60 friends of friends algorithm. And so looking in 6-dimensional phase space, so 3 positional dimensions and 3 velocity dimensions, then just looking at which particles are most similar to each other, and then you can effectively form groups based on that. And as well, you can have groups within groups, as this kind of toy example here shows. And so what we want to do then is go from an n-body simulation, which is much more computationally easy to run because you're not having to include stars, neutrinos, black holes, gas, anything like that. It's just dark matter. And then, based on the properties of the dark matter, be able to infer something about the galaxies which sit inside the dark matter, and we can basically paint a load of galaxies into that in-body simulation. And machine learning is a fantastic way of doing this. So just give a little bit of background on the machine learning techniques that I use. Here's a really kind of easy to understand example just to set us up here. So if you've got a decision tree, that's just a way of categorizing data. And so based on some properties, you can split in one direction or another. And the points at which these split and on what properties are then optimized, and that's how the machine learns. And so, say for our example here, the temperature right now is about 30 degrees, and it's pretty sunny, so we can go down the tree and say, oh, it's weather to wear a t-shirt. Great. And then you can go one step further from that, and if you have loads of trees rather than just one, you can then aggregate the results of the trees, and that does tend to improve the predictive capabilities of your model. And this is called a random forest. And you can use this for both regression and for classification problems. And so if you want to do a regression problem with a random forest, you basically take all the outputs from your decision trees and find the mean of all of those, and that gives you your output. Or if you want to classify some data, you could say take the most common class that the trees have selected. And so say, for my work, you want to take in some properties of the dark matter, and particularly what I'm interested in is then making a prediction on the stellar mass. So based on this, we could just kind of naively go, oh, let's take in our dark matter properties, so the dark matter mass, and some information about the mass density in the local environment around the halo. And as well, another thing that's very useful is information about the maximum of the circular velocity profile of the dark matter. And then we could just put this into a random forest regressor and get an estimate. And that's pretty good, but it does come with some issues. So if we look at the stellar mass function of our training data, we can see for that lowest mass bin, which mostly corresponds to halos which have no stellar mass in them, we've got 4 orders of magnitude difference between, say, the next highest bin. And in fact, in the FLAMINGO halo catalogues, about 40% of the dark matter halos do not have any stellar mass in, which makes for a very unbalanced data set. And there's a couple of reasons why this occurs. It could just be that the subhalo just actually wouldn't have any stellar mass in, but also it can be due to resolution limitations of the simulations. So perhaps we would expect the halo to have 0.1 particles worth of stellar mass in, which is just going to manifest as no stellar mass. So we can go one step further from that kind of naive model, and then instead have a binary classifier that says, does this halo have stellar mass or does it not? And if we think it doesn't have any mass, there we go, we've got our estimate, it's 0. Or if we think it has got some mass greater than 0, we could then do a regression on the mass to get an estimate. And this is better, but there's still another small issue, because this is good for the individual estimates, but the bulk distributions will have an issue, because what we're doing, as you recall, is taking the mean of all those trees. And so if the probability distribution, basically, of the stellar mass looks something like that, and we're always basically sampling the mean of that distribution, we're going to end up, say for a given dark matter mass, the distribution of stellar masses that we get as a result of that is narrower, the conditional stellar mass function, and that's a very important property for these models, which then are used for being able to use observations to constrain cosmological parameters. So we would like to preserve the conditional stellar mass function. So instead, what would be nice to be able to do is not estimate the mean of this, but estimate the whole probability distribution and then sample from that distribution. So what instead we could do is bin the data by stellar mass, use a classifier, and then each tree is going to estimate which bin of stellar mass the halo exists in, and then that'll effectively give us a kind of discrete distribution based on all of the trees together. So they will give us a distribution that looks something like this. So say for 500 trees, that 12% of them estimate that most predicted bin. And then what we could do, this looks pretty Gaussian to me, is we could then fit a continuous distribution to it, so that then that gives us something we can sample from, rather than just having only the number of bins amount of possible values. So that continuous distribution will then give us an estimate for the stellar mass. And so then this gives us our overall model architecture. First, we estimate whether the subhalo has any stellar mass. If we believe that it will have stellar mass, we can then estimate the probability distribution of the stellar mass using that classifier, fit a continuous distribution to that discrete distribution, sample from the continuous distribution, and that gives our estimate for the stellar mass. So how well does this work? Well, pretty well, I think. So this is the stellar mass function overall, and we can see, so the blue is the classifier, the orange is the regressor, which does still include the initial binary classifier as well. And then the green is the ground truth flamingo values. And we can see we get very good agreement here, which is encouraging. Do note that there are regions on the far left and far right here which it looks a bit weird. So on the far left, that's because of the resolution limitations of Flamingo. You're getting to areas in which there might only be 1 or 2 stellar mass particles. And so then that causes issues. And then at the higher mass end, there's very few galaxies of that mass. And so then the sample used is very small, and so then the models are not so effectively predictive in that region. But in the central region, we can see that they're very effective, and we've got very small residuals on the stellar mass function. And now I mentioned the conditional stellar mass function earlier. So looking at on the left there, so that's the dark matter mass on the x-axis, and then the mean stellar mass on the y-axis, and the error bars correspond to the standard deviation of the stellar mass function at that given dark matter mass. And we can see these look very similar. And to illustrate what I'd mentioned earlier, if we say look at a given small range of dark matter mass, we can see that the regressor gives us a much narrower distribution than we'd like, whereas the classifier gives us a much more similar distribution to the ground truth in Flamingo. And again, we can see this for a different dark matter mass range. So that's really encouraging, that what we wanted the model to do, to be optimized for, is able to reproduce. And as well, there's some other things that we get for free as well, like the NN correlation function, so effectively the probability of finding galaxies, just numbers of galaxies as a function of distance, of length scale, is recovered as well, so that's very good. So just to conclude, find that machine learning is a really effective way of modeling that connection between halo dark matter properties and the stellar mass of galaxies that sit within those halos. And we're able to reproduce bulk distributions as well, like the stellar mass function and the NN correlation function. And we're able to preserve the conditional stellar mass function by optimizing the architecture of the model so that it would estimate the probability distribution and then sample from that. Thank you all for listening. Take any questions.
Thanks for your nice talk. So, do you have any measure of uncertainty for your model?
Yes, I mean, it's possible to compare the overall similarity to the ground truth simulations. I mean, it is not so trivial to get like an uncertainty, but we can see the at least like very high correlation between the data and the produced by the model and the FLAMINGO results. But yeah.
Thank you for the nice talk. I wanted to ask, how does your approach compare against other tools to model the galaxy halo connection? I'm thinking, for example, of subhalo abundance matching or semi-analytical models, things like that.
Yeah. So, for example, like subhalo abundance matching, the great advantage that this has over subhalo abundance matching is that you can take in many more features of the subhalos, and so a classic one to do for a subhalo abundance matching would just be to have a relation between the maximum of the circular velocity profile and the stellar mass. And so we do then find that the results are improved by including more features.
Are there cosmological applications of what you are doing?
I think it's useful for enabling cosmological statistical analysis. That from this you can then it gives as I mentioned earlier, simulations that can then be used to calibrate a halo model that then can be combined with observations to then say produce constraints on something like S8, for example. So it's very useful for galaxy clustering.
Thanks. Let's thank Eliott again.